chapter 11, and we will hopefully be finished it by sometime next week. So it's a lot of work, isn't it? There's a lot of stuff in this. We've at least finished the tests, right? There are no more tests. So now we're going to look at a thing that's called a power series. So I'll tell you what a power series is. Power series is essentially an infinite polynomial. Wow, an infinite polynomial. You would think you would think that an infinite polynomial would not be that interesting, you know, because it goes on forever. What possible use could you have that? Well, here's an example of an infinite polynomial. A0 plus A1x plus 2, that guy, and A3x cubed forever. That's a power series. Well, what do they guys look like? Well, we tend to write power series like that. Do you notice that the counting variable n starts at a 0? Well, it's a little cosmetic, but it does. And can you imagine that this, using sigma notation, would generate that? Great. If you plug in n is 0, you get a0, x to the 0, which is 1. So that gets you this term. You plug in 3, right, n equals 3, you get a3, x cubed. And when you have a power series written like this particular power series, when they look like this, are called Maclaurin's series. So if you ever see a power series with this format. Now, an is typically going to be some function of n, right? It's going to be 1 over n cubed or e to the n over n factorial or something, right? It's going to look like that, typically. Of course, a little bit less obviously, there's an even weirder version of a power series that looks like this fella. And when you write this in sigma notation, it will have that form. You're comfortable with how this power series would look like that. My A's look like 9s. I apologize. Sometimes they look more like 9s than they do as A's. When it's written, if the power series is written like this, it's called a Taylor series. Centered at x equals A. So I'm just getting you used to the terminology. So there are two basic power series. Either it's a Maclaurin series or it's going to be a Taylor series centered at x equals A. In fact, isn't a Maclaurin series just a special case of a Taylor series? What special case is a Maclaurin series? What special case of this guy is that guy?
A is 0.
Yeah. So if you have a power series centered at 0, aren't you basically just looking at a Taylor series? But it's also called Maclaurin series. And I think that's for historical reasons. Maclaurin series were created and analyzed first. People looked at, I wonder if we could get anything interesting from an infinite polynomial. And you will be amazed at what cool things come from infinite polynomials. Things you wouldn't even dream of actually exist. And later, the guy Taylor came around and tweaked it a little bit, because for some situations, you can't really have an infinite polynomial centered at 0. So let's show you an example of one. Here is Maclaurin series. Agreed? Now, in this particular Maclaurin series, isn't the AN that piece? Agreed? Now, X is a variable, right? It's a polynomial in X. X is a variable, right? It can take on for different values. Don't you get different series? So for instance, if I said that X was 2, wouldn't this become just a normal series, wouldn't it? Agreed? So what we are very often interested in, and actually this is what this section is going to deal with, is for what values of X does any given power series, right? For what values of X does it converge, right? Well, you agree this can, well, trust me, this guy here, right? Does he converge? Do you know just looking at it? Any gut feelings? Does this converge or diverge?
I think it diverges.
It does. But if I took X equals 1/2, the power series I would get would be that one, and this one converges. Now, if you wanted to find out, does this converge or diverge, couldn't you simply do, in this case, I would do the divergence test because its limit is infinite. And if I was wanting to prove that this one converges, couldn't I do an alternating series test, right? So I could do tests to prove it, but doesn't that tell us that there are some values of X where this diverges and is of no use to us, and there's others where this actually becomes a number? And so the two things that we are going to be trying to find, first thing is called the radius of convergence. And it's normally called R, and R is a positive number. And the second thing we're going to find is called the interval of convergence. I, and I is an interval I is an interval. So you might have a power series where the radius of convergence is 4 and the interval of convergence is from 0 to 4, right? An interval where as long as X is numbers between 0 and 4, the power series will converge. And we're really only interested in when do power series converge? If you have a power series for a particular value of X and it diverges, that's not very interesting because it just means you can't use the power series, right? The answer is infinite. So let's find R and I, because that's essentially what a lot of the questions are going to be. So here's my first one. I'm going to find the radius and interval of convergence of this power series. What shall I do? That's boring, that one, don't want that one. Can I find an interesting? Let's do X to the N over N squared. Yeah, Pick a nice simple one to start with. Now, if I want to know when this thing converges, I have to think of X as being a number. Now, which of all the tests that we do you think would work well with this particular series? Which test should I use to see if it converges? So I want you to think of X as 5 to the n. Right, that may help.
The ratio test?
Let's do a ratio test. And by the way, try and always do a ratio test first before you make your life hard, right? Because they tend to lend themselves really, really well to the ratio test. The vast majority will be that. Now and again, yeah, I might do an nth root test, okay? Just now and again. But ratio test is your go-to guy. So let's remind you how that works. It's going to be the limit as n tends to infinity of a to the n plus 1 over a to the n with an absolute value around it. That absolute value is crucial now, and it should never disappear. You know how in some of the earlier questions I said the top's positive and the bottom's positive, so we'll just ignore it. Don't do that anymore, because X will be negative in some cases, in which case you can't guarantee that the thing is positive. So keep it always. So it's going to be the limit as n tends to infinity. Right, if you replace this with n plus 1, you essentially get that guy. And then on the bottom, oops, you get that guy. Which now becomes this guy. So far, so good. Ratio test. Turn the second guy upside down and multiply. So pretty cool. Right. In this particular case, I'm just going to do the n squared and FOIL this guy out. Is there any cancelling that we can do between these two terms?
The x into the 1. No, the x to the n plus 1 becomes just x, and it, yeah, cancels out with the other x to the n.
And it's left on the top. Agreed? Everybody comfortable? I just made it red to emphasize it, but we're good. Now, I tend to, because these are notes and things you want to look at, I tend to do these kind of separately. Let's focus now on the n squared plus 2n plus 1. What does the, forget about the x, but what does that piece as n goes to infinity, what does that get you? 1. Agreed? Could you prove it by doing L'Hopital? Could you prove it by dividing the top and bottom by n squared? Can we say that you've proved it? And 1 times the absolute value of x is the absolute value of x. Are we comfortable with that bit? Because it'd take me forever if I wrote everything else down. Now, what we've found is that the limit of the ratio is that. Aren't we interested in when it converges? Great. And it converges when this limit is less than what number?
Less than 1.
Right, less than 1. And we have now discovered this guy called the radius of convergence. And the radius of convergence is whatever that number there is. As long as this says absolute value of x, then it's what this number is. So can you imagine a different question where the absolute value wasn't the absolute value of x, but it was 4 times x, right? Something like that. So can you imagine in a different, I'll try and make one where that happens. You get to the end and the answer looks like that. Then you would divide both sides by 4 and you'd get that. And now the radius of convergence would be a quarter. Can you imagine another story where you might get that left over, right? It's always going to start with less than 1 and then you tweak it. Now, to get the R value, you have to reduce it to this format, right? The absolute value of X less than whatever the number is. So if this happened, couldn't you divide both sides by 2? And then couldn't you take essentially the square root of both sides? And so in that case, R would be this fella, or if you made it look pretty, that guy. Are you comfortable about how the radius of convergence is found? You do the ratio test, you simplify it out, and you will get something with an X in it. It might just be X, that was a nice simple one, but maybe it's absolute value of 10X or a half X. And from there, you can then do one extra step if you need to get it to be the absolute value of X on its own. And whatever number you get, that is called the radius of convergence. So far, so good? Right, now back to the one that we did get. Very simple one. We are now going to get the interval of convergence. It's called I. Back to this guy. Won't this series, right, this power series, won't it converge as long as this is true? Right, so as long as the absolute value of X is less than 1. Well, doesn't that mean all the values of X from -1 to 1? Agreed? Absolute value of X is all the values of X between -1 and +1. Remember the absolute value, the positive numerical value of something. Now, that's not the final answer, although it may end up being that. Right now, there's no guarantees because we have the little sticky issue of boundaries. If this is equal to 1, right, the boundaries, right, the intervals here and here, there are 2 special cases that we need to check. We always need to check. And these are the boundaries. In this interval, the boundaries are X equals -1 and X equals 1. You agree? The endpoints, the boundaries. And what I need to do is I need to check these 2 guys with the original power series. Can you imagine there might be a situation where when X is 1, it converges, and when X is -1, it doesn't, right? Which means that I will tweak the ends. What I will do, instead of a curved bracket, which means you can't include it, I'll turn it into one of those square brackets that means you do. This last step, a lot of people forget to do it, and there's a lot of points there. So I'm going to start by doing my first check. X equals -1. Well, when you plug -1 in here, the power series ends up being that guy. Now, if I had time, I would prove this, but I hope you can look at that and say, hey, that's an alternating, right? An alternating series. Would you agree that's an alternating series that converges? I mean, just looking at it, can you kind of tell it's going to work?
Yeah.
Can you trust me it does? Right. So it's a converger. Now, if I replace it by 1, we get 1 to the n over n squared. Well, you know, 1 to the n is really not a nice way of writing it. Couldn't you just call it 1? Because 1 to the power of n is going to be 1, isn't it? 1, 1 squared, 1 cubed, 1 to the 4th. Do you recognize that as a power series? Sorry, it's a p series. P value of 2.
Yep. And P it converges because
And it
P is greater than 1.
Agreed. Now, back to our guy. This is our final answer then. The completed interval of convergence. We originally found that it was definitely going to be numbers between -1 and 1, but we weren't sure what the boundaries were. Well, when I checked -1, it converged, and when I checked 1, it converges. So that means the interval of convergence is square brackets in both sides. Did that make sense?
So when we check it, and if they both converge, then we put square brackets around that.
right? And if one of them fails, you put a curve on that side. So you could have 2 square, 1 square and curved, both curved. Any one of those can happen, right? And what we are now saying is that for this power series, you will be able to get a numerical answer as long as you use values of x between -1 and 1, including -1 and 1, right? You're allowed to use those. If this had been the real answer, it would be a very similar result. This power series converges as long as you use numbers between -1 and 1, but don't use -1 and 1, right? You can't use the endpoints of boundaries. And I haven't really, and I don't want to yet, explain why these are so cool. It's a bit like telling you the end of a movie. Kind of spoils it, doesn't it? So right now, I'm just making you do stuff for no apparent reason, except, you know, it's a power series and you can find out things, right? But you'll discover how useful these power series are and why you would want to do this later. So let's try another example. Just a little bit more messy than this one. Not 100%, just a tweak, but enough to make a difference. And we're going to find the interval and radius of convergence again. So it's going to be this fella over this guy. So -1 to the n plus 1, 2 to the n plus 1, x to the n plus 1, all over n plus 1. And on the bottom, -1 to the n, 2 to the n, x to the n over n. That is a downright ugly looking thing. So it's going to be this guy. And this guy. The absolute values always stay. Never rub them out in a power series. So let's save a line of working. Anybody in the top cancels out with anybody in the bottom. You see anybody in the top cancelling with anyone in the bottom?
Two and x.
Yeah, the
Yeah.
2 and the x would both cancel.
Okay, so if they do this one cancelling with this, would you agree there's a 2 left? All right. If we do to the x to the n plus 1 cancelling with the x to the n, would you agree that there's an x? Right. Here's a little trick because it's always going to work. Do you see this -1 to the n plus 1 and this other -1? Technically, they cancel and you would have a -1 left over in the top. But if you take the absolute value of -1, doesn't it basically destroy it? So what I'm saying is, you can just pretend that the -1s weren't there, right? They're going to disappear. And so what we're left with is a 2, an x, and an n, and then another n plus 1. Now, forget about these two guys. You should be able to look at that fraction and say, yep, I know what that's going to be. What will the limit of that be as n becomes infinite?
1.
1. So would you agree that in this case, we get that? Are you comfortable if the limit as n tends to infinity of this is that? Now, according to the ratio test, won't this converge when the limit is less than 1? And remember what I said earlier? Sometimes, and this is one of those sometimes, don't you have to reduce the thing to tell me what the absolute value of x has to be less than. What is the radius of convergence now? What number is the radius of convergence?
1/2.
1/2. Yeah, just to show you it's not always 1, right? You can see it being a different number. Now, our initial interval of convergence is going to be what values of x is this true for? And would you agree it's -1/2 to +1/2? Agreed? Right? The values of x that have an absolute value less than 1/2 are values of x in this range. And the interval of convergence is always going to be a start to a finish guy, right? You don't get one of those, it's the outside, right? It's the bigger versions. It's always that. Now that means then that don't we have to test both boundaries? Because maybe one of them, it will also converge. So the two boundaries are going to be x equals -1/2. And that means that this power series becomes -1 to the n, 2 to the n, -1/2 to the n, all over n. And we want to find out if that series converges or not. And you very often can come a cropper with the algebra. This guy is nowhere near the way it needs to be written if I'm going to simplify this. I have to find a better way of breaking this up. Any suggestions on how to break this thing up?
Would it be completely ridiculous to suggest merging all of the powers of n on the numerator?
Could be. I'm not sure what you mean. It might be okay. Depends what you mean.
I
Tell me
just
what I
think it's all
should
like
write.
it should be like a number to the n, and then can't you merge like the 2 and the -1/2?
Oh, I
n,
see. Yeah, I see.
and then merge that with the -1, and then just end up with a -1 to the n.
Well, not quite, but you're very close. Similar to what you just said, I've taken this guy and separated it into -1 to the n times 1/2 to the n. Are you comfortable with that way of splitting it? So far, so good? Now we'll do that putting them together, which is what I heard. If you take -1 to the power of n and you multiply it by another -1 to the power of n, what power of -1 do you get? It's the same answer if it was 5 to the n times 5 to the n. What would you get if you combined -1 to the n with -1 to the n?
Or -1 to the
2n.
2n, right? Agreed? Now, what would you get if you took 2 to the n and multiplied it by 1/2 to the n? And if that jumps too much, I'll show you an in-between step that might help. But 2 to the n multiplied by 1/2 to the n. Okay.
1 to the 2n.
Sure, that would work. See if I can. Actually, wouldn't the answer just be 1? You agree? So 1 to 2n basically is 1. So I'm not going to write times 1. Maybe I will. Now, this one is going to maybe freak you out. What number, and it's a single number, no powers of n, what number is -1 to the 2n?
One.
Well done. Yes, nailed it. Why?
Because the 2 is going to make any number double, which is going to make the -1 become basically -1 times -1, which is going to nix the negative.
Yeah. Isn't it going to be -1 to an even power, and aren't even powers -1 to an even power just 1. So that makes this guy this guy. Do you recognize him now? Told you it's a lot of work. You recognize that guy? P series, P equals 1 diverges. Well, if you do a half, right, that's the other boundary, you will get n equals 0 to infinity, -1 to the n, 2 to the n, times a half to the n, all over n. So far, so good. Now, things are just a little bit different here. Would you agree that 2 to the n times a half to the n basically cancel each other and you get 1? So you've got -1 to the n times 1, so I'll just do that, and I'll have this guy. So that guy cancels down to this fella. Are you happy with the 2 to the n cancelling a half to the n, right? They're cancelling, they become 1, right? And 1 times that guy is just that guy. It's not 1 to the n, it's not -1 to the n, it's just a number 1. If you want 1 to the n, just call it 1, right? So you get that guy. Does that guy converge or diverge? -1 to the n over n. Converge or diverge?
Converge?
Yeah, it's a alternating series that converges. Now you put that into our package. At the -1/2 side here, it doesn't work, but at the +1/2 side, it does work. So our interval of convergence, I, is going to be curved at this side and square bracket at that side. So can you imagine when you're doing your homework, you have to make sure that you check the boundaries? Because you see in this case, the boundaries are different, right? One is curved and the other is square. Because at -1/2, you can't, it doesn't work, right? It diverges. But when x is 1/2, it does converge. We cool on that? So let's show you some other situations that can happen when you want to find R and I. Oops. Suppose we do this one. Keep it nice and simple. X to the n over n factorial. Well, we're going to do our ratio test, as you kind of know. That's pretty much what all of them, with a very few exceptions, are going to be. And so it's an n+1 over an n+1. Don't know what that's doing there. Factorial. Oh. Are you comfortable with me skipping ugly fraction divided by ugly fraction and just writing first fraction times the upside down guy? Are you happy about there to there without needing the big ugly fraction now? Hopefully there's going to come a point in time where I don't need to write this guy and just write this one. Have you noticed it's basically bottom guy turned upside down? And that'll save you a whole load of writing, and me a whole load of writing if I can do that. Well, let's see what happens as far as cancelling goes. This is becoming kind of second nature. Don't those two cancels and you're left with an X on the top? Isn't that very common? Now, hopefully you haven't forgotten about factorials. But an n factorial on the top will cancel an n+1 factorial in the bottom. What's left and where does it go, top and bottom? When an
n+1 on the bottom.
Are we all comfortable with that's what that simplifies down to? Now, once you get to this stage, don't you pretend x is a fixed number, right? So it's just 5 or something, right? Oh, this is interesting. What's the limit of this going to be as n becomes infinite?
0.
It is, isn't it? 5 over infinity, or x in this case. So brute force, the answer is 0. Wait a minute. If the limit is 0, and it's always 0, regardless of who x is, doesn't that mean that this is clearly less than 1 all the time?
So it's always convergent.
So it's always convergent. And we would say R is infinity. Does that make sense, that the radius of convergence? It's just like a number that says how big from 0, right? R is like the value from 0. You know, if you imagine negative R to R, isn't that what the interval of convergence looks like, right? How far away from 0 can you go? So if you can do everybody, isn't it infinite? And would you also agree that the interval of convergence is very easy, because isn't it minus infinity to infinity, everybody? So that is a really nice power series, isn't it? Because for every value of x in the universe, it converges. Some of the other power series, don't they just have little windows, 1 to -1, a half to -half, that kind of one? That's kind of restrictive. This is like the ultimate version of very nice. But actually, this power series is really cool when you find out about what it is. I mean, it's a nice simple one, but it's really cool what it does. Let's show you another extreme. Do that one. So it's going to be the limit as n tends to infinity, ratio test. It's going to be the limit as n tends to infinity. No, that's not what I wanted. I'm going to have to change this a little bit. Yeah, that'll work. So it's going to be e to n plus 1 squared times x to the n plus 1 over n plus 1 times an n and e to the n squared and then x to the n. And I'm going to rewrite this fella here a little bit differently. And while I'm at it, I'm going to rewrite the order on the bottom so that the top and the bottom match, right? And that's just cosmetic. You can shuffle them any way you like. Now, let's do some cancelling and see what happens. Can't really do much to that right now as far as cancelling goes, so I'll just leave it alone. What would this guy cancelling with that guy gets?
X.
And X on the top, right? Non-special going on there. Right. The reason I had to spend a little bit more time was in this one because it's pretty ugly. E to the n squared plus 2n plus 1 on the top cancels out with an e to the n squared. What is left?
N plus 1.
Great. E to the power 2n plus 1. So far, so good. Now, since this one's a little bit ugly, I'm taking a lot longer than perhaps you might think I need to. All I'm doing there is kind of combining some stuff. Now, that guy's fixed, so we don't need to worry about him. And this one, you're going to have to trust me. If you make n go infinite, what do you think n e to the 2n plus 1 over n plus 1 equals? And you could do it by doing L'Hopital's rule. And if you want me, I'll show you L'Hopital's rule. But what's your gut feeling? What does that horrible fraction become? A big infinity, as Matthew's trying to draw, or a cat with eyes and ears? Could be the alternative, right? you we comfortable that that's infinity, or do you want me to see? You want to see the proof of it?
Could you show the proof of it?
Sure. So I promised you L'Hopital would do it. So let's show you how that would work. Well, if you do L'Hopital, you're going to differentiate the top and the bottom, right? Well, differentiate the bottom, you get 1. To differentiate the top, you're going to have to do the product rule. So if I call this F and I call this G, you get F dash, which is 1, so you get this guy. And then you get N times the derivative of this guy. And you get an extra 2. So what you're looking at is the limit as N tends to infinity of e to the 2n plus 1 plus 2n e to the 2n plus 1. Again, I'm taking more lines than you probably need. Couldn't you brute force that? Isn't it e is infinity times 1 plus infinity, which is clearly infinite? Convinced? Bit ugly, but it works. But that means this is infinite. So if I do brute force, aren't I going to have infinity times an x? But isn't an infinity times an x infinity? So it looks like that when you do the ratio test on this, the answer, no matter who x is always going to be infinity. Well, doesn't that mean that it's never going to converge? Well, it seems that way, right? No matter what x you pick. There is one exception, and that's why this question does have an R and an I. Back to the original. If you made x 0, wouldn't every single one of these numbers be 0? And wouldn't adding an infinite number of zeros still be 0? So technically speaking, isn't x equals 0 always going to work, no matter what you do, right? So a power series will always converge when x is 0, because when x is 0, everybody's gone, right? Now, what do you think? Oh, the interval of convergence here is a little bit strange. Couldn't I call it 0 to 0? With a square bracket, I should say. That's a really weird thing. I would probably just say x equals 0. What do you think the radius of convergence would be in this question? Yes. So haven't we seen both extremes here? We've seen the extreme where everybody works, right? Radius of convergence infinity, interval of convergence negative infinity to plus infinity. And we've seen power series where essentially nothing works, right? Except a very trivial case when x is 0. And when that happens, your radius r is 0 and your interval of convergence is a square bracket from 0 to 0. Or just write x equals 0 as the same meaning. Are we good? Right. Got time for one last one. I'm just randomly going to pick something. Something from the homework. Well, why not? Question 2, it's in front of me. And in this particular one, it starts at 1. And power series can start at any number they like, as long as it's positive. Little side issue. Why did this power series start at 1 instead of the typical 0? What's the problem with 0? N equals 0.
You can't divide by 0.
Right, so that's it. Can you imagine sometimes a power series might have to start at 2 for some reason or other, right? It's okay. Doesn't change one darn thing, right? Same process. So the limit as n tends to infinity of the first guy divided by the second is going to be the limit as n tends to infinity of negative 1 to the n plus 1, x to the n plus 1, and this guy here is going to be the cube root of n plus 1. And then you turn everybody upside down, you get that. Okay, a little bit ugly cancelling, but essentially, can't we just forget about negative ones? They disappear because the absolute value. Can't this guy cancel with this guy and leave an x? So I'm now looking at the limit as n tends to infinity of the cube root of n over the cube root of n plus 1 x. Okay, that's a very ugly looking fraction. Do you know what the limit of that ugly fraction would be as n goes infinite? It's actually quite an easy conclusion. 1. Right, you want to prove it, couldn't you stick them inside a big cube root and do the cube root of n over n plus 1 and then do a divide top and bottom by n trick? That's actually the only way I can think of proving that's 1, and it is 1, which means we get that guy, and that guy is less than 1. So we are looking at a radius convergence 1 and a possible interval of convergence of negative 1 to 1, right? Don't have time to finish it, I just looked at the clock there. So here goes. If you plug 1 into here, you get that guy. Do you reckon that an alternating series that converges? So if you plug in x equals 1, it works. If you plug in negative 1 here, this negative 1 to the n and that negative 1 to the n combine, and they give you negative 1 to the 2n, which Maggie mentioned earlier is positive 1, right? Negative 1 to 2n. Isn't 1 over the cube root of n a power series that doesn't converge? So on this side, you get negative 1. And that would be the end of that question. Whew. Bit fast, but we got there. And, oh, thumbs up, Dylan likes it. So that's us. Say your last name as always, and bye-bye, and I will see you tomorrow. I'll hang about for the question. Matthew, are you still here? No, he's gone. Matthew's going to have to work on his infinity symbol. I mean, doesn't that look like a cat? So, you know, he's not here, so it's not as much fun making fun of him. But when he comes next week, Maggie and Kira and Wendell, will we all go like that for infinity, just to see if he pays attention, right? Oh God, yeah, infinity cat. Right, that's it. We should have a math cat, and its nickname is Infinity Cat. Bye bye, guys.
Professor,
Yes, Jed.
real quickly, could I look back at the proof for
The L'Hopital proof
e
one?
to the the L'Hopital proof? Thank you.
Yes. Here is this it? No, it's not that. It's here, so I will find it eventually. Not that
No
one.
worries.
It was always going to be the last one I check, wasn't it? I might have to go back and see if I two stuck together then. Would you believe it? That's probably what's happened. Yeah, not that one. Keep going. Here it is here. Put it on the screen. You can't see it. So it was n e to the 2n plus 1 on the top over n plus 1 on the bottom. I did a L'Hopital on it. Differentiating the bottom was easy. You got 1. To differentiate the top, I used a product rule. So that was f, and this piece here is g. So it's the derivative of n, which is 1, times leave g alone, plus leave f alone, and then differentiate e to the 2n plus 1, which is where that extra 2 came from. So the top row is this guy plus 2n e to this guy, and then pulled out the e to the 2n plus 1 as a common factor. And then I brute forced it. E is infinity times 1 plus infinity. And infinity times infinity is just infinite. And that means that that limit is infinitely big. Does that work, Jade?
Yes, perfect. Thank you. I was just missing a line, so I ended up looking at it like not completely understanding it. Thank you so much.
Not a problem. Glad to
Have
be
a good
of
rest
help.
of your day.
You too. Okay, any other questions, guys?
I have a question about that was on this weekend's test.
No problem. What was it?
It was number 6. It was basically -1 to the power of n on top, and then 2 to the power of n on the bottom, and then ang factorial.
That guy?
Yeah, and we're supposed to estimate how many terms we're supposed to use.
Right, to get what kind of accuracy?
I believe it's accuracy to the 5th decimal.
Okay, so we'll show you the method. If it's not, it's the method will be right. So 5th decimal place means that an plus 1 should equal 0.1, 2, 3, 4, 5 zeros and a 5. Remember, you move to the next place and stick a 5 there. Now, e to the n plus 1, I really don't need to worry about the negative parts. All I need to find is that guy. Now, you should try, if possible, to solve this algebraically, right? But it ain't always possible. Right? I can't solve equations with factorials in them by factoring or algebra. All I'm going to do is the old guess and check method. So, give me a number less than 10.
5.
So, I'm going to do n equals 5, and I'm going to see what that is. And if it's a number less than that, that's a good sign. Although it's probably going to be called 5e to the negative 6, right? Because when you go small, it goes that way. So it's going to be 1 divided by, put a bracket around it, 2 to the power of 6 times 6 factorial, because 5 add 1 gives me 6. So 6, math button, numerical computing. There we go. Choice number 4. Okay, finish the brackets. So that would be n equals 5 is this fella. So it's 1 over 2 to the 6, 6 factorial, and enter. Whoa, that was lucky. 2.1 times e to the negative 6. Now, agreed? Which is actually, isn't that a little bit smaller than what we need? I should check n equals 4, just to be sure. So it's 1 over 2 to the 5 times 5 factorial. And so I'll just bring that back up and change that guy to 5 and this guy to 5. And boom. And oh, that's not good enough. So there's the guy you need. And there's your answer. 5 terms.
Okay. And so the whole, where'd you get the 5e to the negative 6?
From the calculator. I went and calculated this.
That was just his example, the 5e to the negative 6.
Oh, okay.
Oh, this here,
Yeah.
I turned that guy into scientific notation so that I'd be able to compare it to what the TI-84 is going to call it.
Oh, okay. Right, yeah, that was my question, because I was on the test, I was just trying to solve it like algebraically, and I was like, I don't know what I'm doing.
I mean, I could try, but I don't think the calculator can handle factorials. I mean, I could do it on I could try and do it. I don't think it's going to work, but I'll try it. I could just go here and say 1 divided by, basically call that x, so it's going to be a bracket, 2 to the power of x add 1
I tried it on Desmos and I don't think it worked out.
Did it kill over and die?
Yeah, a little bit.
Yeah. It wouldn't surprise me. That's 2 to the power x plus 1. I'm even going to have a problem trying to put in the factorial because I'm worried in case it thinks it's part of this power. I guess if I put a bracket around it, that might save it. And then another bracket and go x plus 1. Yeah, I'm going to kill this. This is not going to work, but I've started, so I'm going to finish. Okay. I'll do a window starting at 0 and finishing at 5. And then I'm going to do a zoom 0 to zoom fit. See if we kill the calculator. Wow. I seem to just have some random dots. Would you agree it just killed over and died? So, you know, it's a bit like that game. You guess a number too big, you guess another number too small. Eventually, aren't you going to narrow it down? That's the number that works. And
Okay.
what number works? Whenever this is at least as smaller than that, right? And this one here wasn't any good because I think it was an e to the -4 or something, which is far too big.
All right.
Okay.
Yeah. Thank you.
Right.
That was the main question. Thank you.
Right. Next, any other questions?
Yeah, I had a question about the homework and then on the test that happened again, where they had us comparing B sub n with B sub n plus 1.
Right.
And I was confused where that came from because I didn't remember talking about it in class.
We do. There's a proof that it's decreasing. Remember when you do alternating series, you prove it's decreasing. And you prove it by finding this guy and showing it's negative, right? Well, when they say Bn plus 1 is less than Bn, that just mathematically means it's decreasing. So when they're doing that, if you can prove it's decreasing, you're just trying to prove that. It's they could have said, prove that. All you would do is put, I think in that question, do you just put a symbol like less than or greater than? Yeah, you have 50-50 chance of saying it the right way around. But that's all they're meaning, that you've proved that it's decreasing. WebAssign's not very good at being able to give you opportunities to show working, right? Because what you would be doing there is a derivative thing. So hopefully that kind of makes sense. Now you said the homework question.
Yeah, I was just, it was the same thing.
Oh,
Yeah, but it was
okay.
on both the homework and the exam.
Right, so same answer, right? That, you know, if you didn't get that, I don't think you should be too worried. It's just WebAssign's way of saying, show me it's decreasing. Because what's that saying is that the next term is smaller than the one that came before, which is decreasing.
Okay, that makes a lot of sense. Thank you.
You are welcome. Are we done for today, or is there any other questions? I'm going to be in the office, sir. I think I don't have any meetings today. My hope is I don't. So I'll see you there if you have any more questions.
Thank you. Have a good day.
You too. Bye-bye, guys.